I am Dr. SASILATHA, Professor and Dean heading the Department of Electrical and Electronics Engineering. Today we are going to discuss about the topic called CMOS design. It is one of the important topic in digital logic circuits that we are going to discuss. To understand the basic operation of CMOS structures, we need to talk about NMOS transistors and PMOS transistors. NMOS transistors are N-channel metal oxide semiconductor field effect transistors, and PMOS transistors are P-channel metal oxide semiconductor field effect transistors. So, if you look at the MOS transistor theory, in NMOS transistors, the channel will be established with the help of electrons, and in the case of PMOS transistors, channel will be established with the help of holes. The bulk structure available in NMOS transistors are P-type semiconductors, and in the case of PMOS transistors are N-type semiconductors. And also source and drain are developed with the help of N plus heavily doped NMOS semiconductors. In the case of PMOS transistors, again the source and drain are made up of heavily doped P-type semiconductors. Both NMOS and PMOS transistors will work depending upon the bias applied to the gate. There are two modes of operation of PMOS transistors as well as NMOS transistors. In PMOS, it is operated both in enhancement mode as well as in depletion mode. Even in NMOS, it is operated in enhancement as well as in depletion mode. Let us consider an NMOS transistor. We can apply bias to the gate. The gate bias may be either negative bias or positive bias. In the case of NMOS transistors, if we apply positive bias, that is if the threshold voltage is greater than 0, naturally electrons will be induced in the channel. So, more electrons will be flowing in the flowing between source and drain. This is in the case of NMOS transistors, and the PMOS transistor, the gate potential will be negative, so that positive electrons will be induced in the channel. So, the carriers will be flowing from drain to source or from source to drain, and the conduction of current will be taking place in the transistor. In NMOS transistor, it is operated in enhancement mode. The gate potential is greater than 0, so that naturally more electrons will be induced in the channel. Depending upon the gate potential, the transistor will be either on or off. In PMOS transistor, that is P-channel metal oxide semiconductor field effect transistor, the channel will be established with the help of holes. So, the applied potential to the gate will be negative. We can draw two different characteristic curve either from NMOS transistor as well as from the PMOS transistor. They are drain characteristic curve and transfer characteristic curve. If we look at the drain characteristic curve, it is a curve which is drawn between drain voltage and drain current. And if you look at the transfer characteristic curve, with respect to VGS, that is gate to source voltage, what will be the current that you can see, and in enhancement mode, the operation of the current will be less, and in the depletion mode it is more in the case of PMOS, and it is reverse for NMOS. The structure of depletion type PMOS transistor, we can see here the channel is depleted of mobile charge carriers based upon the gate to source potential. So, here also you can draw two different characteristic curve. One is drain characteristic curve, which is a curve which is drawn between drain voltage and drain current, and also the transfer characteristic curve we can draw. IDS is the current at VGS equal to 0, that also we can view in the next slide. With the basic concepts in mind, we can formulate logic structures from CMOS. So, basically there are various types of logic families. Best one is static CMOS, another one is dynamic CMOS, third one is pseudo NMOS. And here in digital logic circuits, let us try to understand static CMOS. In static CMOS, we can have PDN as well as PUN that you can view. In static CMOS, upper half of the structure is made up of PMOS, that is PUN network, pull up network, and lower half of the structure is made up of PDN, that is pull down network. Pull up network pulls up the output voltage to VDD, and pull down networks pull down the output towards 0. You can see in the top, that is in PUN, we can view the number of PMOS transistors, and in PDN there are number of NMOS transistors. Here the MOS transistors which are connected in series as well as in parallel is shown for various gates. Say for example, if it is for CMOS inverter, there must be one PMOS transistors at the upper half of the structure, and there must be one NMOS transistor at the lower half of the structure. The gates of both the transistors are tied together and a common input has to be given to the gates. And you can see if the input voltage is 0, output voltage will be high. Similarly, if the input voltage is high, output will be 0. This shows the basic structure of one CMOS inverter. Whenever the input voltage is 0, output will be high due to the current conduction of both the PMOS as well as NMOS transistors. And also you can see the characteristic curve, that will be inverted output. Similarly, we can derive the logic structure for other gates such as Nand, NOR, then what else, XR, XNOR, other structures also can be derived. In this particular slide, you can see the AND gate, how the transistors will conduct depending upon the input signal voltage. The NMOS transistor always passes positive voltages and PMOS transistor passes negative voltages. So here, if A and B are connected in series, output will be equal to the input, that is Y is equal to X. If A and B are connected in parallel, output is equal to input, so that we can get OR structure. So this slide shows both AND as well as OR structure using MOS transistors. One is established using NMOS, the same also will be established using PMOS. PMOS switch closes if the control input is low. Here you can see the two PMOS transistors are connected in series. So if the input voltage is high, accordingly we are able to get the logic output. Y is equal to X if A bar and B bar, that is equal to corresponding logic. Similarly, for the next structure, you can see both the transistors are connected in parallel, simultaneously you are able to get the output. This shows both AND logic as well as OR logic using PMOS. Both are connected in series as well as in parallel. Similarly, you can derive NAND gate. You need 4 transistors, 2 transistors are NMOS transistors and 2 transistors are PMOS transistors. If 2 transistors are connected in series, the corresponding output will be either high or low. You can look at the truth table. Whenever the input A is equal to 0, B is equal to 0, the output will be 1 for NAND gate. Similarly, for 0 1, it is 1, 1 0 1, 1 1 0. This is for the truth table of 2 input NAND structure using CMOS. Like this, you can have a NOR gate, XR, XNOR, that we are going to discuss one by one. The logic behind NOR will be Y is equal to A plus the whole complement. You can see the truth table of NOR structure based upon the number of inputs. Here we are seeing 2 input single output NOR gate. If both the inputs are 0, output is 1. If one of the input is 0, output is 0. If both the inputs are 1, output is 0. This is the truth table of NOR gate using CMOS. In CMOS, we are using both PMOS as well as NMOS. PMOS is in the topmost part, that acts as a pull-up network, and NMOS acts as a pull-down network. Look at a complex gate. The output is equal to D plus A dot B plus C, the whole bar. Let us try to see how we are going to derive the CMOS structure. As I mentioned earlier, the top part will be the pull-up network, which is constructed using combinations of PMOS, and the lowermost part, that is pull down network, is constructed using combinations of NMOS. So, in this case, since we have D plus A dot B plus C, first you will have to draw PMOS transistor, CMOS transistor, which has to be connected in series in the topmost part, and again A transistor will be connected in parallel, since it is equal to A dot B plus C, and D transistor is connected in series. The entire structure is connected in series with the T transistor. This is applicable for the pull up network. For pull down network, it is reverse. That is, you can have B transistor and B transistor and C transistor in parallel. That will be connected in series with A transistor. Then the entire structure is connected in parallel with D transistor. So, the complex gate called D plus A dot B plus C is evaluated using CMOS. As I told, CMOS is a combination of both PMOS and NMOS, that is derived in this slide. Here you can see a 4 input NAND gate. So, naturally you need 8 transistors. They are 4 NMOS transistors and 4 PMOS transistors. The connections will be established in such a way that the transistor will conduct current depending upon the input signal voltage. As we discussed earlier, PMOS transistor conducts if the input voltage is low and NMOS transistor conducts if the input voltage is high. So, based upon this, you can have the 4 input NAND gate. In pull up network, all PMOS transistors are connected in parallel, and in pull down network, all NMOS transistors are connected in series. So, you can view the layout of the corresponding structure, that is also available here. Any gate can be simulated using tools such as either microwind or Tanner or any other simulator what is available. So, with the inputs in mind, you can get the output. Even simulated output also you can get for all the gates. So, let us discuss about pseudo NMOS logic, since we know the basic of static CMOS. As we discussed earlier, there are various logics available that is very useful for implementing any digital circuits. Digital circuits are established or they are all implemented using VLSI, very large scale integrated circuits. So, in this CMOS technology is the better technology, as we all know. So, this is the next logic, which is nothing but pseudo NMOS logic. Pseudo means false. Here the pull up network is replaced using one PMOS. The gate of the PMOS is grounded. So, I can say that PMOS always conducts depending upon the input signal, that is low voltage. Now, here we are able to get the output depending upon the input combinations that is being applied to PDN, that is pull down network. Pull down network is established using NMOS transistors. NMOS transistor conducts depending upon the input signal voltage. So, the output of the pseudo NMOS logic, what we are trying to get is with respect to the inputs. So, in pseudo NMOS logic, say for example, if you want to establish one inverter, naturally PMOS acts as a load that is acting as a PUN, that is pull up network, and in the PDN network we have one NMOS, only one NMOS is required. We are able to get the inverted output. And for AND gate or NAND gate, you need 2 NMOS transistors that has to be connected down. Naturally, we are able to get the output. Similarly, for NOR gate, the 2 NMOS transistors has to be connected in parallel. We will get the output. So, we can verify the truth table of the NMOS, NAND gate or AND gate, whatever it may be, based upon the input combinations which is being applied to the lower part PDN network. One example is given here, pseudo NMOS. Here 4 transistors A, B, C, D. 4 transistors are connected in parallel. So, now we can understand the output of this logic. The PMOS transistor conducts current since the gate of the transistor is connected to 0. So, it always conducts, it acts as a load, current will be flowing through the device. Now, whenever A transistor is 1, B transistor is 1, C is 1, D is 1, all transistor conducts, output will be 1. If one of the transistor is 0, then also remaining 3 transistors will conduct, output will be 1. If all transistors are 0, that is input will be 0, then only output is 0. So, this is the logic behind pseudo NMOS. You can relate pseudo NMOS as well as static CMOS. How will you relate? The difference is in static CMOS, PUN is consisting of PMOS. There are combinations of PMOS, but in pseudo NMOS, the PUN is consisting of only PMOS. This is the only difference. other things are all exactly similar, and in pseudo NMOS it has its own advantages and disadvantages because it occupies less area, low input gate load capacitance. See, these are advantages of pseudo NMOS, and for by considering the other logics we are able to get very good advantages. So far we have discussed static CMOS, pseudo NMOS. Let us try to understand the differences between static CMOS and pseudo NMOS. Static CMOS consists of both NMOS as well as PMOS. It occupies more space. So, you know, in VLSI there are three challenges. One is area. It occupies more area. Static CMOS occupies more area. Then simultaneously power dissipation, that also will come into the picture. Power will be dissipating more in static CMOS when compared to other CMOS structures, because there are number of transistors involved depending upon number of inputs. Say for example, if you consider Y is equal to A bar, or for inverter, let us consider an inverter. If A is the input, Y is the output, it is equal to A dash. So, depending upon the number of inputs, the number of transistors will vary. If the number of input n is equal to 1, then number of transistors required will be 2n. For inverter, it is 2n, that is 2 into 1. So, you need 2 transistors. 2 transistors, one transistor is NMOS transistor, another transistor is PMOS transistor. This is for inverter. For AND gate, you can see the AND gate. If there are 2 inputs, Y is equal to AB, and for NAND gate, it is AB the whole dash. So, the number of transistors required will be 4, because 2 multiplied by the number of inputs are 1 plus 1, 2. So, you need 4 transistors. The 4 transistors are 2 NMOS transistors and 2 PMOS transistors. Similarly, for 3 input NAND gate, let us consider 3 input NAND gate. 3 input NAND gate. If A, B, C are the inputs, Y is equal to A, B, C, the whole dash is the output. So, how many transistors are required? 2n, 2 multiplied by 3. So, how many? 6 transistors is required. So, in static CMOS, you need more number of transistors. So, it occupies more area. Naturally, the power dissipated in the circuit is also more. To avoid all these such issues, we are going for other types of logics, that may be either pseudo NMOS or dynamic CMOS or pass transistor logic. There are other logics are also available, that we are going to discuss one by one. Okay. So, in pseudo NMOS, you can have VDD rail, ground rail. Let us consider one inverter again. If A is the input, Y is equal to A dash is the output. Whenever A is 0, output will be 1. Whenever A is 1, output will be 0. So, in this case, let us consider one PUN, that is pull up network will be the PMOS. The gate of the PMOS is grounded, and here we have the pull down network. For inverter, you can consider one NMOS transistor. Output you can take at this point. So, here whenever A is equal to 0, you will be getting output as 1. Whenever A is 1, output will be 0. Why it is called as pseudo NMOS? Here the PUN network is false, always it is on, because the gate potential is connected to 0, gate voltage is 0. So, this is on, naturally it acts as a load or it conducts, Accordingly, depending upon the input, we will be getting the output. Okay. So, you can, how will you differentiate static CMOS and pseudo NMOS? Static CMOS, we have more number of transistors, it occupies more area, naturally power dissipation will be more. In pseudo NMOS, it has its own advantages, number of transistors are less. Let us consider one NAND gate, maybe 2 input single output NAND gate or 3 input single output NAND gate. So, in this case, we are going to draw the structure right now. Let us draw one VDD rail, that is a supply rail, ground rail, upper half of the structure consisting of only PMOS. The gate is connected to ground, and lower half we have A as well as B transistors, which has to be connected in series. A, B, and this is the output. So, if you look at the structure of the transistors, you can see for AND or NAND operation, both transistors will be connected in series. So, if it is for NOR, both has to be connected in parallel. Accordingly, we are able to get the output, and let me try to explain the truth table of this particular gate. A, B, Y. You know the combinations of A and B, that may be either 0, 0, 0, 1, 1, 0, 1, 1. So, what is the output? If A is equal to 0, B is equal to 0. 0 means the transistor will not conduct, because both transistors are NMOS transistor. This is NMOS, NMOS. Whenever the input voltage is 1, the transistor conducts, otherwise it will not conduct. So, depending upon the combinations of A and B, you can see output is 1. How will you get the output? These two will not conduct, but this transistor will conduct, it acts as a load. So, the potential available at VDD rail will be available at the output. Similarly, it is suitable for the second case as well as third case. In the second case, when A is equal to 0, this will not conduct. B is equal to 1, this conducts, but naturally there must be some gap, or it is open circuited. So, naturally the output will be established at this point. So, it is equal to 1. Even for the third case also it is 1. Fourth case, if both the inputs are 1, so here it conducts, so all the current will be flowing towards ground. You cannot take any output at this point. So, that output will be 0. So, this is the structure of pseudo NMOS. Using pseudo NMOS, we can construct this NAND gate. This will be applicable for 3 input NAND also, that we are going to see right now. For 3 input NAND gate, first you have to draw the symbol of NAND gate. It has got 3 inputs. Let us consider the inputs are A, B, C, followed by a bubble, Y is equal to A, B, C, the whole dash. We can draw the structure, draw a VDD rail, ground rail, then draw one PUN, pull up network, which must be the PMOS. It has to be grounded, and ABC transistors has to be connected in series. They are all NMOS transistors. These transistors will be connected in series. A, B, C, output you can take Y is equal to ABC, the whole dash. Let us try to understand this structure with the help of a truth table. You can draw the truth table A, B, C, Y. The combinations of inputs you can draw, they are all 0, 0, 0, 0, 0, 1, 0 1 0 0 1 1 1 0 0. You can write all the combinations of inputs, zeros and ones. 1 0 1 1 1 0 1 1 1 1 2 3 4 5 6 7 8 different combinations of inputs, and you can see how we are going to get the output. For 0 0 0, what is the output that we are going to find out from the structure? Let us apply 0 here, 0 here, 0 here. The meaning of this is you are giving active low input to all transistors. Naturally, the transistors will not conduct. The potential applied at this point will be available over here since it is on. So, it is 1. Here also, if any one of the transistors input is 0, right, 0, output will be 1 only, because for this case also, if it is 0 0 1, output will be 1, because one of the transistor does not conduct. Even though other transistors will conduct, since one of the transistors will not conduct, it is naturally it is open circuited. Whatever potential is available, the potential will be available at this point. So, for all these cases, I can write 1 1 1 1 1, and for the last case, if you apply 1 1 1, these 3 transistors will conduct. So, output will be 0. Why? Because since all transistors conduct, whatever potential is available here, that pass towards ground. So, you cannot take any output at this point. So, naturally it is 0. Okay. So, this is how we can derive any circuit. Whatever I have discussed is only for 3 input NAND gate. The same thing is applicable for NOR gate also. That also we can see right now. 3 input NOR. You can have the structure slightly different. Y is equal to A plus B plus C the whole dash. You can have the same truth table, and here the transistors A, B, C are connected in parallel. So, let us draw the transistor. This is A, then another one is B, third one is C. So, all the 3 transistors are connected in parallel. So, A, B, C, you can give the inputs, that may be either 0 0 0 or 0 0 1 or 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 or 1 1 1. So, if you apply the combinations of inputs, what will be the output that we can see? Say for example, for the first case, if it is 0 0 0, it will not conduct. So, this part is open circuited. So, output will be equal to the potential across this one, or it is equal to VDD. So, it is 1. And for the second case, if it is 0 0 1, one of the transistor conducts, right. If one of the transistor conducts, even though you do not bother about A, B, okay, because these two are open circuited, what is the potential across this point? This point will be 0. And for the third case also, 2 transistors will not conduct, only one transistor conducts. So, the path is close, it is 0, here also 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 it is 0. If all transistors are 1, that is, if the gate voltage of all transistors are equal to 1, what will be the output? All transistors will conduct. So, naturally all will be going towards ground. The potential, there is no drop at this point. So, naturally it will be equal to, there is no potential. So, it is equal to 0. So, this is for pseudo NMOS. 3 input NOR gate is shown here. The same thing is applicable for other complex structures also. Let us see a function f is equal to A plus BC the whole dash. For a complex structure, f is equal to A plus BC the whole dash. How many transistors are required? 3 transistors are required. You can have the combinations of both the NOR gate as well as NAND gate. So, in this case, we can have this pseudo NMOS structure. The structures, how many transistors are required? 3 plus 1, 4. 4 transistors are required. Now, I can draw that structure also. BC, BC, A, so A plus BC, F is equal to A plus BC the whole dash. So here the transistor A, B, C, B, C are connected in a series. So B, C, B, C are connected in series, that A will be connected in parallel. Output F or Y is equal to A plus BC the whole dash. So how many transistors are required for implementing the function F is equal to A plus BC the whole dash? 1, 2, 3, 4. But if you consider the static CMOS, naturally the number of transistors will be more. 2n number of transistors are required. So in this case 6 transistors are required, but here only 4 transistors are required, but we are able to get the proper output even if it is connected like this. So here we can give the input and we can take the output. So here it is A 0 plus BC the whole dash. So 0 plus 0 the whole dash is, you are supposed to get 1. Let us try to see whether you are getting 1 at the output. A is 1, sorry, A is 0, so this will not conduct. B and Z 0, this will not conduct, but the PMOS transistor will be conducting. So output will be equal to 1. Then for the second case, for 0, 0, 1, since it is 0, one of the transistor will not conduct, so output is 1. Next 0, 1, 0. For 0, 1, 0, A is 0, this will not conduct, and here one of the transistor conducts, another one will not conduct. Naturally output will be equal to 1. And for this case, for 0, 1, 1, A is 0, this will not conduct. You look at B and C, both transistors will conduct. So path will be established, current will be flowing through the device. So naturally you cannot take any output over here. So output will be 0. Even if you give the input over here also, you can see Y is equal to A is 0 plus 1, 1. 1 dot 1 is 1, 0 plus 1, 1, 1 complement is 0, that you are getting is correct. And for the next case, for 1, 0, 0, A is 1, so this will conduct. 0, 0, this will not conduct. So naturally the path will be established. So for this case it is 0, this is also 0, this is also 0, because A is 1, A always conducts. Since A is conducting, okay, so what will happen? The current will be flowing through this device. Even if B is 0 or 1, we do not bother. Only we are going to follow only A. Okay. So in this case, the current flows like this. It is very difficult for you to take any output over here, so naturally 0. And for the last case, 1 plus 1, the whole complement is 0, because everything is conducting, is 0. So this is how we can implement any circuit using pseudo NMOS. There are other logic structures available, that also we can discuss one by one. So the logic circuits will be implemented using VLSI. One of the logic is static CMOS, another one logic is pseudo NMOS. There are other logics are also available, dynamic CMOS, fast transistor logic, then other logic such as PE logic, everything is available, that we will be discussing in the other sessions. Thank you for listening. Thank you.